Good afternoon, everyone. Thank you for joining us. You are here for the Unit 4.2 Energy Transfer and Electricity Unit Overview. My name is Janita Vasquez. I am the Elementary Curriculum Manager here at Open SciEd, and joining me today is Candice Gaigaitan, who was the revision lead for this unit. So I am excited to have her here with us to help us share everything about this 4.2 unit. Can you go to the next slide, please, Candice? All right, so let me tell you a little bit about how we're going to move through this afternoon. First, I'm going to tell you a little bit about Open SciEd Elementary in case you are not familiar with all our fantastic materials. Then Candice is going to take over and walk us all through our phenomenon anchoring lesson and start us off in this unit. Then Candice is going to give us a tour of the storyline so we get to learn a little bit about every single one of the lessons in this unit. And then she is also going to tell us about some key features, and these key features are pieces that Candice is just really excited to share about this unit, and we hope you'll be excited about these things too. I am going to start, and I'm just trying to make sure that everyone has their mute buttons on, if you can, and we'll get going. Slides and handouts can be found in the bit.ly. I just posted it in the chat. Also, if you have questions throughout the webinar, please post them in the chat. We will get to them at the end of the presentation. And if I find a question that must be answered while Candice is in the middle of taking us to the unit, she will be lovely and stop for us and answer that question. Otherwise, I will try to tackle most of the questions on my own, and we'll revisit them at the end of the presentation. So just some quick things about Open SciEd. Open SciEd is an innovative nonprofit organization. We bring together amazing people to help us develop free, high-quality science instructional materials and professional learning materials to go along with instruction, with our curriculum. Next slide. We had 9 partner states help us in the field test of these units. We are actually currently field testing our very last unit, Unit 4, and we've partnered with over 450 teachers to help us do that field test. Next slide.
Al parecer, Matilde les
Right,
dijo.
so just a little bit about our materials. And first of all, just want to tell you, this is our instructional model. And Candice is going to go through the instructional model, explain to you so much more about it. But our units are built using this model in which students engage in asking questions about some interesting phenomenon, and they use those questions to drive instruction throughout the unit. All our units are connected in service of making sense of a puzzling phenomenon and being coherent and making sense from the student's perspective from the beginning to the end of the unit. Next slide, and then the one after that. One more, Candice. All right. Oh, there they go. So our units are designed for real classrooms. You can see all the lovely covers here for our 4 units. While we offer a recommended sequence, we built these units to be flexible and to be modular so that you could choose when they fit best in the school year and what works best in your schedule. Next slide, please. Right, so again, because we are designed for real classrooms, I want to give you just a quick overview about our units. In each grade band, in each grade, we offer 4 units that make the full curriculum. In K2 and 3-5, the number of lessons is different. In K2, those lessons, there's 10 of those lessons, and each of those lessons is 60 minutes long. Now, in Open SciEd, we think of a lesson in a different way. This is not a one point in time, one lesson, one day, because no one in elementary has 60 minutes in one day to be able to finish a lesson. So our lessons spread across days and maybe even weeks, depending on what your science teaching schedule looks like. In K2, that adds up to 2,400 minutes of instruction per year, which is only about 4.5% of the instructional time for a typical year of school. So this is totally doable. We're really trying to think about what time you have available to teach science. In grades 3 to 5, we offer up to 15 lessons per unit. While our design specifications call for 15 lessons per unit, we also make sure to tell the authors that if they can get the work done in 13 lessons and 12 lessons, then there's no reason to fill extra lessons in the materials, because again, we're thinking about you. So if we were to write all of those 15 lessons per unit, that would equal 5,400 minutes. So that's only 10% of a typical school year. And again, these are 90-minute lessons that are not meant to be taught in one shot. They're meant to be scheduled throughout the week or across weeks, depending on what your science schedule is. Next slide. We believe strongly in integrating math and ELA into our materials. Anytime that you see math in Open SciEd, that math is there to help us make sense of the science that we're learning. You are never going to see math for the sake of having math. It is always to think about how it helps us make sense of the science. We integrate math using lots of math talk, using math modeling, but where we focus most of our time is in developing data concepts. So from kindergarten to 5th grade, students are gathering data, analyzing data, talking about data. That's really important to us. And we know that it's a skill that everyone needs for their whole life. Next slide, please. We also do a lot to support literacy in our program. Our units include a collection of student books and other texts that were developed by our authors. So you never have to think about having to order separate materials or when, a book's license runs out or any of those things. And all of our text is informational. So it's always about thinking about gathering new information, learning vocabulary, and encouraging different ways of communicating. In Open SciEd, we believe it's important for students to communicate their knowledge of science in lots of different ways. That may include using English. It may include using gestures, using drawings, using noises sometimes, and when necessary, encouraging students to use their home language. Next slide. Right, we also offer a comprehensive assessment system for each of our units. As you can see here, these are all the types of assessments that we offer, but this isn't all of it. We don't want to ever hand you an assessment on your own. We want to make sure that you have rubrics, that you have samples of student work, that you have supports when thinking about after you gather that data from an assessment, what happens next? What do we do instructionally? All of those supports are built into the materials. Next slide. All right, and you hopefully already know that you can find all of our materials on our website. But if you're looking to have printed materials, or if you're looking for kits, for materials kits, we have many partners that help us do that work. And you can find connections to their websites from our website. Okay, we have several vendors that are helping us with this work. And I believe, next slide, Candace. Oh, yes. And this is when I hand it over to Candace to tell us all about 4.2.
Well, welcome everybody. Thank you for joining us today. I am Candace Gaitan. I am a research scientist and curriculum developer with BSCS Science Learning. And I had the pleasure of getting to be a writer on the pilot test version of this particular unit, and then leading an amazing team of folks to help with the revision and public release of this unit 4.2, Energy, Transfer, and Electricity. So I do want to acknowledge that I had a lot of folks working with me on this unit. I had a team of co-writers, team of teachers and reviewers at every step of the way that really helped to make this a meaningful, coherent, and engaging unit for students. And I am very excited to share with you what this unit is all about today. So as I take us on this journey into the 4.2 unit, I am going to highlight how each of the lessons relates to our storyline instructional model that you see here. This is the instructional model upon which all of the Open SCIED units are built. And we're going to kick off our introduction by spending a little longer talking through the anchoring phenomenon lesson, because this is what launches our learning and what motivates us to want to know more about electricity. And all of the units that use this storyline instructional model, the first lesson should introduce an interesting phenomenon or problem by way of giving all the students some sort of shared collective experience for us to see and observe and wonder about. We provide an opportunity for students to share our initial ideas about what they think caused this phenomenon or problem to occur. And we also want to motivate students to ask questions, to investigate and answer throughout the unit, because in an Open SCIED unit, students are the ones who are determining the investigative pathways that we take. And we also, for teachers, want to provide a pre-assessment opportunity so that they can see what their students' prior knowledge is coming into this unit, so that we can really build from those foundational understandings that students have. So with that, let's jump in to our anchoring phenomenon lesson together and see how we launch this unit. So we start our anchor by posing a few questions to students. We ask them to consider what they use to tell time and if that device has ever stopped working. Students may say something like, I use the microwave to tell the time, and sometimes it comes unplugged. I use my caretaker's phone and the battery dies sometimes, and so I can't see what time it is. Or I use my Xbox and my brother unplugged it. We then introduce students to a winding clock and have them make observations about how it's turned on, how it stays on, and why it suddenly stops. To make our observations, we use our senses and keep track of them using our notice and wonder sheet. We write down what we see, what we hear, what we feel as we get the winding clock to turn on and stay on. We also jot down what we wonder. Students may have ideas like, we turn the winder with our hands. I felt the clock shaking when it ticked and talked. I could hear the ticking with my ears. I could feel the ticking. It felt like it was vibrating. I could hear the alarm go off. It was loud. Students may also wonder, why do we have to wind this? How does a winding clock work? What causes the sound? We then introduce students to a second clock and have them make observations of how we get it to turn on and stay on. We quickly notice that this is a plug-in clock, so that's what we call it moving forward. And students notice that they can feel it getting warmer the longer it's plugged in, that it also makes a sound when the alarm goes off. And then we wonder why we have to plug this clock in when the other one just had to be wound. And why there's a place for a battery. Why does this clock have both a plug and a battery? We realize as we're starting to make these observations that we're actually making comparisons between the two clocks as we talk about them. So we take this as an opportunity to share our observations on a Venn diagram so that we can compare the similarities and differences between the two. And we notice that they both have numbers and can show time, but we think one uses electricity or power of some kind and the other one doesn't. We're really not sure what electricity or power is. We also notice that if you don't wind the winding clock, it won't stay on. And when you unplug the plug-in clock, it turns off. As we create this chart, we recognize that we've identified a phenomenon. Clocks can turn on and stay on in different ways. We also notice that we've identified quite a few differences, so maybe we should just focus on one clock for now. So we create a model of how we decide to create a model of how the plug-in clock works. As a class, we think about what models are and how scientists use them and how we've also used them to communicate our ideas in science or in math. And then we create an initial model to explain, why does the plug-in clock turn on and stay on? To help us create our models, we use our notice and wonder charts from when we made our initial observations and also our class Venn diagram. Before coming together as a class to share our models, we first share them with a partner and then make some revisions if we want to, if our partner had some really good ideas that we may have missed. We then come together in a scientist circle to create a class consensus model of how the plug-in clock turns on and stays on. To help us create our model, we use sentence starters that can help us have a conversation with one another. This helps us to make sure that we are building from one another's ideas. It also helps us to ask questions because we may not always understand what our peer has communicated to us, and we may not always agree, and that's okay. Disagreement helps us to identify things we might want to investigate further. And this is our class consensus model. We labeled the components we think are important, like the outlet in the wall and the plug we put into the outlet. We have some questions about why we can hear alarms and why the clock also needs a battery, so we put some question marks next to those components. We also identify that we can push buttons to change the time and that we think power is coming from the wall, but we don't really know what that is. Maybe it's electricity. And we, again, aren't sure what electricity is either. So we put a question mark there. Using these uncertainties that come up when we developed our model, we write down our questions on sticky notes to share with the class. We then organize our questions to help us, and we use our model to do this. So we put our questions on our model so that we can see exactly where our questions were that can help us sort of figure out what we were seeing and wondering. And we have questions like, where does the power come from? What does this plug do? What causes the clock to feel warm? What turns the light on? And if we put a battery inside, what happens? We have a lot of really great questions that need answers. So we brainstorm ways we can answer our questions and then share with the class. We decide that we could read a book, we could watch a video, we could dissect the clocks because taking things apart is a lot of fun. We can try a battery in the clock and see what happens. We can look at other things that plug in or other things that turn on in different ways. And we can look at different plugs and see how they work. So using some of these ideas and ideas for investigation, we make a decision of where to go next. And we decide that we want to start by identifying other devices that turn on so that we can start to see if they turn on and stay on in ways that are similar to the plug-in clock or maybe slightly different from the plug-in clock. So we decide to go look outside our classroom, in our communities, wherever we may be, and jot down some ideas. And then we're going to share those observations when we come back together in our next class. And that is our anchoring phenomenon lesson. We make observations of a winding clock and a plug-in clock and compare what we think makes them turn on and stay on. We use our observations to develop a model of how the plug-in clock works and what makes it stay on so that we can continue to use it. We generated and organized our questions about how the clock turns on and stays on, and we brainstormed ideas for investigation. And we even figured out what to do next. We want to figure out and find other examples of devices that turn on, like the plug-in clock. And that last piece is a really integral part of the storyline instructional model. We call that a navigation. We decided together collectively as a class what we need to do next. And we as designers do that so that the unit is coherent from a student's perspective, because we want students to see that they have agency to develop ideas and consider what needs to happen next in order to further our learning. So as a class, we now have a shared mission to figure something out. And the sequence of work in this unit helps them to make progress on answering their questions. The ultimate goal for us is that if someone were to ask a student experiencing this unit to come into a classroom and tap them on their shoulder and ask them, what are you doing today? The student should be able to connect back to their own questions about this phenomenon. The student would hopefully say, we're trying to figure out how a plug-in clock turns on and stays on, rather than just saying, my teacher said this is what we're doing today. Oop. There we go. So now I'm going to give us a tour of the rest of the unit so that we can see how all of the lessons are now connected and how we build from the anchoring phenomenon lesson that students experience. And as we do that, I'm going to continue to highlight how each lesson fits into our instructional model. And what you will notice, if you are not already familiar with an OpenSciED instructional model, is that most of the lessons in a storyline unit are investigation lessons where students engage in science and engineering practices, where they collaborate to create a where the teacher provides students with opportunities to grapple with, figure out, and make sense of science ideas. So let's jump into our first investigation lesson. And I just got a note that my internet is unstable. So if I'm cutting out, I'm sorry. So what I'm going to do is I'm actually going to turn off my video for a little bit while I walk through this, but I'll still be able to see chat. You'll still be able to yell at me if you need me. Okay, so in lesson 2, an investigation lesson, we bring our ideas of things that are like the plug-in clock, and we also take a school tour to find other examples of things that turn on. We notice that we can tell things are on because they move, they light up, they cause us to feel heat, or they cause sound. We dissect, we then decide we want to see what's inside the plug-in clock, because that's the next thing that we're going to need to really help us make progress on what we want to figure out. We dissect a plug-in clock as a class, unplugged, of course, and notice there's a lot of parts that are all connected by wires. We then wonder if there's wires inside the winding clock too. So we look inside a transparent winding clock and see that it's very different. But unlike the plug-in clock, we can see what's happening to make everything move. So we create a model of our winding clock. And this is important because, as Janita pointed out earlier, we've created these units to be sequential or modular. So for any students who have had Unit 4.1, as we develop this model, they will probably start to use phrases like energy from my hand causes the winder to move, or energy is transferred from the winder to the gears. So this particular modeling activity can serve as a review of concepts from 4.1. But for students who have not yet had 4.1, this is an opportunity for students to develop the ideas of what are energy and what is energy and energy transfer. So using our model of the winding clock, we notice that there are things happening that cause changes inside the winding clock. Our hand causes a change in the spring, which then causes a change in motion in the gears, which causes a change in motion in the clock hands. We learn that energy is the ability to do something or make a change, and that it can be transferred from place to place, like from our hands to the winder. We then wonder if the wires inside and outside the plug-in clock are transferring energy to make it work. We take another look at our plug-in clock and think about places where energy could be coming from, and we notice that battery holder again. And we think we've heard batteries give energy to things. So we decide to explore if batteries can transfer energy. So in our next investigation lesson, we make observations to gather evidence for how a battery makes a light shine. We build understanding that electricity is energy transferred through electrical current. We also build an understanding that electric currents have to flow in a complete path for the energy to be transferred. Once we figure out more about batteries, we return to our plug-in clock model and revise it to include where energy is coming from and where energy is going and how it is transferred. And again, for students who have had 4.1, this is something that they will be really used to doing, but this is an opportunity for students who have not had 4.1 to really learn how to track where is energy coming from, where is energy going, and what is our evidence that energy has been transferred. We then begin to wonder about how electricity is getting into the outlet in the wall so that it can even be transferred to a device like a clock. We decide we want to investigate that further. So in our lesson 4 investigation, we have questions about where the electricity is coming from to make our plug-in clock turn on and stay on. So we tour the school with the custodian to find our answers. We trace the wires from our classroom to the school's electrical panels to the power lines coming in from outside. We make connections between our observations and the ideas we've been figuring out so far. And we figure out that the wires or paths that bring electricity into our school and classroom begin somewhere outside the building. And if the power lines get broken or disconnected, the electricity does not have a path to travel on and things turn off. We update our consensus model, then read a book to see and hear how power outages may happen in different communities. We update our driving question board and identify that we still don't know where the electricity for the building comes from. How does it get into the wires that come into our school? So in this next investigation lesson, we want to know where electricity comes from. So we start by investigating how wind can generate electrical current. After making predictions about what we think could be happening, we make and discuss observations of a small wind turbine lighting an LED in our classroom. We decide we want to know more about how larger scale wind turbines and wind farms generate electricity, so we read a book and watch a video to find out more. Then we explain how a wind turbine generates electricity and identify some possible limitations on its use. Now we're wondering about other ways that electricity is generated, because we notice a limitation of wind turbines is that the wind doesn't always blow. So what else can we do to generate electricity? That navigates us into another investigation lesson where we wonder what we can do about generating electricity when the wind doesn't blow. We research different methods for generating electricity that use resources other than wind. We notice all the methods for generating electricity involve changes in motion, except for solar panels, which don't seem to use any moving parts. That leaves us wondering how we can use the sun to generate electricity if there's no change in motion like we've observed in all these other energy sources. That leads us into another investigation. So in lesson 7, we plan and carry out a fair test investigation to gather evidence about how solar panels can generate electricity. We test solar panels by attaching them to a motor and then placing them in light and dark areas. And we also gather additional evidence from text. We figure out that solar panels only work in the sun, so light must be transferring energy to the motor. This is a huge aha moment for us. because we realized that light can transfer energy, and it is also evidence of energy transfer because we can see light coming from the numbers on our plug-in clock. We now have a lot of ideas, and we need to take some time to put them all together and see if we can explain how devices get energy they need to work, like a clock that tells us the time. So at this point in the unit, we need to take stock and see if we can develop a fuller explanation of the unit phenomenon. So it's time for a putting the pieces together lesson. We're going to connect the ideas we figured out from the last several lessons and to see if we've answered our unit question. And in this case, we're going to be answering a question about how a device turns on and stays on. So in lesson 8, we are ready to explain how a device like a plug-in clock turns on and stays on. We revise our class consensus model and create an evidence bank for identifying energy transfer, where we list all the evidence and examples from our investigations. We then apply our understanding and identify evidence of energy transfer to explain how a game console turns on and stays on. We then revisit our driving question board and notice that while we can explain how devices like a plug-in clock turn on and stay on, we can't explain why some clocks always have the right time, even after they've been turned off and turned back on. Like when our phones die and then we turn them back on, they still have the right time, but we had to reset the plug-in clock. So how do these kinds of devices have the right time and never have to be set? This wondering about how some devices always have the right time leads us into another set of investigations. In this unit, we call this part of lesson set 2. And I just turned my video back on, so if I start to cut out again, please let me know. Okay, so in this next lesson, our first investigation lesson in lesson set 2, we recall that we were wondering about clocks that always have the right time, and we decide to explore ways to communicate information across a distance, since that's what clocks do. They help us know what time it is from across a classroom, for example. And we hope that by engineering solutions to this problem, that it can maybe help us figure out how some clocks always have that right time. So we read a book to see and hear how other people use the same engineering design process that we are going to engage in. And then we start by defining our criteria and constraints for our design problem. And then we work in groups to develop a design solution. We start to develop design solutions for communicating time from one person to another in our class. And then once we have our designs, we decide it's time to test them and see if they work. That takes us into lesson 10, where we build and test our design solutions that we planned for last time to see if they can communicate time across a distance. We also finished reading our book about gaming controllers to see and hear how engineers optimize their design solutions. And we use data from our tests then to refine our solutions in larger groups, and as a class, consider how our design could be optimized. Finally, we create our new designs and test them. We then compare our solutions to devices that always have the right time, and we notice something really important. We have some ideas for how information can be transferred, and we've started to notice that it requires energy transfer. We have to use our hands, for example, to maybe push a paper airplane across the room with the time on it, or we have to push a button to turn on a light to communicate the time. So we think energy transfer may be important here, but we want to gather more evidence to really understand what's going on. So we decide to do some more investigating. In our lesson 11 investigation lesson, we obtain information from across multiple station activities that helps us to figure out how some clocks know the time without being set. We figure out that computers use patterns called digital code to think and communicate. We use this information to then engage in a consensus discussion to add to our class consensus model how some clocks know the time. And our biggest aha in this lesson is that all information transfer is energy transfer. We also figure out that digital code is made of on and off patterns represented by ones and zeros, because believe it or not, binary code is a fourth grade standard. And we also learn that digital information is wirelessly transferred using light we cannot see. After updating our class consensus model, we returned to our driving question board and noticed that we still have questions about the effects that plugging in and using our devices may have on the environment. So we wonder how using criteria and constraints can help us evaluate usable energy sources. And I also want to point out here, because I've said it a couple times now, the driving question board in a storylines unit is a really important navigational tool that we can come back to multiple times in a unit and notice that we still have gaps in our understanding to drive some more investigations. So this is just another example of where that happens. So in this lesson, investigation lesson, we want to figure out more about the different effects of usable energy sources and what might happen when we plug in our devices. So as a class, we decide we want to find a usable energy source that minimizes any effects plugging in our devices may have. When we consider effects, we want to think about the plants, animals, lands, waters, and people who may be in our communities. We obtain information from multiple sources to find answers to our questions and evaluate the sources based on criteria and constraints we would want for the energy sources in our community. Then we create slides to synthesize what we figured out and to share what we learned with our classmates in our next class. So in lesson 13, we present to our classmates our findings about the effects of getting and using the energy sources that we researched. Using what we learned from our research and from our peers' presentations, we make a decision about the energy source that we think best fits our criteria and constraints for powering devices in our communities and for minimizing the effects. Ultimately, we recognize this is not a simple problem to answer. It's a fairly complex problem because all usable energy sources have some effects on plants, animals, lands, and people. But we use the evidence from our investigation to make a reasoned judgment that best matches our criteria and constraints. So we have a lot of ideas now about how information is communicated and how plugging in our devices can affect the environment. We now also know how to evaluate energy sources for impacts. It's time we put all of our ideas together and apply our understanding. So this is going to be our final putting pieces together lesson in this unit. And what students will do is they will take stock of their learning across the entire unit and connect ideas they figured out from all of these investigations to apply them to a new problem. And I have to say, this may be my favorite transfer task that I have ever worked on in a unit. But in this putting pieces together lesson, we update our evidence bank for identifying energy transfer to include what we learned about information transfer. So we're now ready to apply our understanding of energy and engineering transfer to a new engineering design problem. We obtain information about a problem that NASA scientists and engineers were trying to solve. A rover designed for Mars stopped working because its solar panels got covered in dirt. When it stopped, scientists were no longer able to communicate with that rover. We used this information to define an engineering problem. We then identify criteria for a good Mars rover and outline constraints that might limit our solutions. We then design a solution and explain how that solution works using our understanding of energy and energy transfer. And finally, we celebrate our learning by revisiting our driving question board and related phenomenon charts, and we look forward to learning more. And that is Unit 4.2 in a nutshell, very quickly. So I just want to take a moment to pause here so that I can take a drink of water. And also, if anyone has any questions about these sets of lessons before I continue on and talk a little bit more about the performance expectations and key features, please put them in the chat, and then we'll try to answer what we can before moving on.
Yes, please feel free to ask any questions in the chat. We don't currently have any questions, Candace. But in the instructional guide, are there tie-ins to the science of reading?
Science of reading. So let me see if I understand what you are talking about. Well, first, let me just say that in all of our teacher guides, there are going to be additional literacy callouts for teachers to provide additional supports on connections to Common Core literacy standards. And we have a literacy team who has done a thorough review of every single one of the lessons ever written for Open SCIED Elementary, and also provided additional guidance for strategies for supporting reading in the classroom. And I believe, Janita, correct me on this if I'm wrong, but I believe there are there's additional guidance in the K-5 teacher handbook as well.
There is additional guidance
Okay.
in the handbook.
Okay.
Joshua, we always talk about anything having to do with literacy we talk about it from Common Core standards. And Eric and Joshua, if this doesn't answer your question, please ask us again. And Eric has a question about assessment opportunities.
Yeah, so I will talk about this a little bit more, so I don't want to give too much away, but I will say that every lesson, there's assessment guidance in every single lesson, in every single unit. So there are formative assessment moments, and we also have lesson learning goals tied to those as formative assessment moments. We provide guidance on how, what kinds of ideas or evidence of student learning to look for related to those lesson learning goals. We also provide suggestions for how to support students if you feel that they are not reaching those particular learning goals in that lesson. And then we also have other assessment moments that I will talk about in a moment that we call key instructional assessment moments. And then we also have the transfer tasks and all related scoring rubrics. But I will go into that in just a moment as well. All right, so I am going to go ahead and move on, but please continue to throw any questions you have in the chat, and then we can answer them again in just a moment. Okay. Standards for Unit 4.2. So now that you have a sense of how ideas are built in this unit, let's talk a little bit about these performance expectations that we're building towards. So we are building towards, this is a meaty unit, as you can see here. The unit builds towards 3 different physical science performance expectations, 1 earth and space science performance expectation, and also 2 engineering performance expectations. I do want to note that PS32, the one listed at the top, is a PE that is also partially covered in Unit 4.1, but that unit only focuses on the sound and heat portion of this particular performance expectation. So we build on ideas from 4.1 to extend our understanding to light and electric currents here in this particular unit. We also are learning to design devices that convert energy from one form to another, like when we design our devices to communicate time. And then through that, we are also engaging and building towards understanding of those engineering, of the earth and space science PE, as well as that other physical science PE. And engage in the 2 engineering design PEs as we define a problem and plan and carry out fair tests to refine those devices. And as we build towards those performance expectations, students are provided supports related to these key science and engineering practices. So I do want to say students engage in all science and engineering practices in this unit, but we do choose to focus a little bit more on some practices in each unit, particularly practices that are tied to the performance expectations in the unit. So we just provide some additional scaffolds and supports for students related to asking questions and defining problems, planning and carrying out investigations, constructing explanations, and in particular, designing solutions, and then also obtaining, evaluating, and communicating information. And then we also very intentionally develop 3 additional cross-cutting concepts, even though we use the others in this unit as well. But we do provide scaffolding for thinking about everything in terms of cause and effect, energy being a very important one for this particular unit, and then also patterns, because we are identifying evidence of energy transfer and recognizing those patterns in different ways across different investigative phenomena. Okay, and so before we give space for questions again, there's just a few more key features of this unit. And these are the things that I'm very excited about this unit in general. I'm sure you can tell, but there's just a few things that I want to share that I really, truly love about this unit and get really excited about talking about. And one of those is the engineering integration of this unit, because it really helps students to unpack questions we know are relevant to their daily lives. So when we first piloted this unit, students were getting really into information transfer aspects of their devices, wanting to know, how does the Wi-Fi work? How do our phones send text messages? How do computers know what to do? So we really wanted to figure out a way to tie that into the revision of this unit in some way, in a way that was bound within the disciplinary core ideas and performance expectations for this unit. And I was so excited because we figured it out by thinking about it in terms of communicating information and information transfer. So we give students these really cool design opportunities so that they can then leverage that to dig into what exactly information transfer is. And students were really into coding and asking questions for coding during the pilot. And because binary code is actually part of one of our performance expectations for this unit, we were able to then figure out ways for students to engage with binary code a little bit as a way to have them think about these patterns of on and offs that drive most of what we do anytime we touch a computer. The second thing I really want to hone in on is related to the question about assessment opportunities. And we really focused a lot on assessment supports in this unit. There are 2 big sets of lessons which students develop some fairly complicated ideas. And so we really wanted to create tools for teachers to use that could help them track student progress on related performance expectations and lesson level learning goals. So those supports include what we call a following student sense-making tool that can track individual student progress and also provides guidance on what evidence of student learning would look for tied to each of the performance expectations. We also have what we call 2 key formative assessment lessons in this unit, and those are really integral moments in student learning. For those lessons, we provide some additional instructional guidance to teachers that are built around ways to further support student learning. And we call these key formative moments because it's a time to really slow down and make sure that students know that students are where they should be before we move on. And the instructional guidance gives additional suggestions for ways to support just a few students, because maybe it's just 1 or 2 students in your classroom that may need a little bit more scaffolding and support. So we give some suggestions for additional activities for just a small group. But then we also give additional activities, for example, if it's maybe the whole class that may need just a little bit more time to unpack and understand circuits, for example, we provide additional guidance and suggestions for how to do that. And then finally, all the transfer tasks in the unit have extensive scoring and rubric guidance to help teachers in assessing their students. And these are just the things that are above and beyond those formative assessment moments that are already built into every lesson. And one more before we open it up for questions. Students interact with a variety of texts in this unit that were created in collaboration with an amazing literacy team. And I really want to emphasize here in particular, the website that we created to help students do their usable energy research for their presentations in lessons 12 and 13. We know how hard it is to monitor students' internet usage in a classroom. So we created a website that has all the information students need, including pictures they can use for their presentations. So it's sort of a one-stop research shop so that teachers don't need to worry about what their students are finding as they engage in this research task. And with that, I'm going to open up for any other questions you have about the unit or Open SciEd in general. Thank you all so much for listening to me talk about this unit.
Thank you, Candace. All right, there haven't been any other questions. I've had some individual chats and direct messaging, but if there are any, Jessica wants to know where she can find the assessments.
There are a couple of different ways that you can access them. So we have one assessment document, and the title of that document is escaping me at the moment. I think it's the
overview.
Assessment overview. And that provides an overview of every single type of assessment that can be found in the unit, and also links out to every single one of those assessments so you can see what they are and what they look like. You can also find them within each lesson. So if you go into the teacher guides for every lesson, you're going to find the assessment guidance page that gives you the lesson learning goal, what to look and watch out for to make sure students are making progress towards that. And that particular box will also link out to the assessments. And you can also find an assessment opportunity call out box in each lesson that is also going to link out to those assessment moments as well. So we really try to make sure that that's accessible in multiple ways throughout the unit.
And that the assessment overview is a separate document. So if you download the unit, it will be one of the things that one of the files you can see in the unit. And then in the teacher's guide, all those pieces have different in the front matter of the unit, you can also find more information. And of course, there's also guidance in our handbook. Joshua has a really great question about some key differences between elementary and our 6-12 program. Joshua, if you send me your email, I can send you a list of those things. There are some differences. The way that we use text in elementary is different. Our use of websites is different. How we link materials in the teacher's guide is different. There's several things. So if you send me your email, I am happy to email you back. And Teresa is asking about, or Teresa is asking about kits. If you look on our website, Teresa, our vendors are there, and they are the best ones to tell you how quickly they can get things to you. They already have 0.1 kids, the first unit of each grade ready to go. The 0.2 units, those are being built right now, but most vendors will turn that around pretty quickly for you. That the students can use so they don't have to Google information. Jenny, the website is included in your teacher materials. It is included in the teacher's guide. There are links there so that you can then give that link to your students to use.
And I will say too, along with that website, we do provide student-facing slides that are also already created for students for that lesson, so that students can just sort of plug and play their information that they want to present to their students. So that is also provided, and that's going to be lessons 12 and 13 where you can find that information.
Okay, so thank you all very much for joining us. Thank you, Candace, for helping us today. And everyone have a good evening, afternoon, depending on where you are today.